Good morning, everyone. My name is Hangdem from Berkeley Lab, and I will be co-chairing this session with my colleague, Professor Jenny Juhan from UIUC. And we'd like to welcome you to our session on probing and monitoring reactive transport processes in Earth systems. We are very excited about this cross-cutting theme because reactive transport processes is one of the most intimately coupled physical and chemical processes in Earth systems, and they play a large role in controlling the dynamic evolution of our Earth systems. That includes natural weathering that shapes the Earth's surface over the geological timescale, as well as processes accelerated by human activities such as geologic carbon sequestration and hydraulic fracturing. To probe and model these processes, we are constantly challenged by the practical need of having field-scale observations and models, as well as the scientific need of really being able to tell something about the mechanistic underlying those processes. That means we have to look at really fine scale as well. And also to capture the intimate coupling of different transport mechanisms, as well as a wide range of biogeochemical reactions, including redox reactions, mineral dissolution, and precipitation, as well as biofilm growth. We have to just use everything in our power, every tool that we have to do it. That includes microfluidic cells, isotopes, reactive transport modeling, definitely. And today, through these 8 invited talks, we hope that you will get a flavor of all those components. And this could be a beginning of more involved and engaged discussions within the community and stimulate more conversations and potentially collaborations. So also, since without me knowing that we have 4 minutes of introductory remarks, I'm gonna, as Jenny suggested, kind of plug in a few advertisement. So there was a REAMG volume on reactive transport modeling, and we'd really encourage you to check it out. It has a lot of exciting recent development in reactive transport modeling involving all kinds of applications and involving different processes. And there's also some very recent publications that we would really like to highlight that includes Lily's recent paper that involves a huge chunk of this community on increasing the role of reactive transport modeling on watershed studies, as well as a recent publication article on elements, right? By Kate Maher and William Meyer on the role of reactive transport modeling. And with that, I think I'm close to the 4 minutes. And I'd like to welcome our first speaker, Professor Sue Brantley from PSU, to give the first talk on what clay and pyrite grains reveal about water and oxygen transport in a shale during weathering. Okay, here we go.
Thank you. Thank you to the organizers and to people that are out here so early in the morning. Including my family who just got here. That's nice. So what we're going to talk about today, hopefully it'll be one of the biggest cross-scale talks that you see while you're here at the meeting. A lot of this work is by my junior colleague, Jin Gu, and you'll see a lot of the work both from the field and to the laboratory. And I just wanted to highlight, what we're really trying to do here was talked about by Rachel Carson, another Pennsylvania woman, about looking at individual grains and trying to relate that to landscape scale, which is one of the things I think reactive transport modeling can do. So I've been fascinated thinking about weathering and reactive transport of weathering, and I'm going to show you a lot of plots that are like this. These are depth profiles. So this is depth downward, and this is how much of a given mineral has been dissolved away by a reactive fluid that's flowed through it. So you can think of this as rain coming into a soil kind of material, and if you start off with no reaction at all, you'd have 0 depletion, you'd plot over here, but then these are time profiles going down here. You would lose some of your mineral with time, so you end up with whatever this is, 70% depletion. Eventually, you're 100% depleted, and then this, what we call reaction front, moves downward with time. And this is a really important characteristic that emerges from all reactive transport models. So dissolution in porous media, what we end up seeing is these localized regions of reaction. And the reaction may move downward with time, but the thickness of the reaction tells you a lot, or the reaction front tells you a lot about the system. And in particular, it tells you something about what the rate constant is, so how large the rate constant is, or the rate constant times the reactant concentration, and something about the fluid velocity. So if the fluid velocity is higher, you can get a wider front, and if the reaction is faster, you can get a narrower front, is one way to remember it. So if I run out of time, this is what I want you to take out of this talk. We can do a lot with reactive transport modeling of 1D weathering profiles. We have a lot of measurements, lots of models. And what we're doing now that's, I think, super exciting is we're looking at these in 2D and 3D, and we're starting to understand how to put them together. So you can see the landscape at the surface of the Earth. We cannot easily see the subsurface landscape of reaction and where the reaction fronts are, but they kind of mimic the surface, and we're trying to map those out in 2D and 3D. I also think that these subsurface landscapes comprise a permeability architecture. So if you have a reaction that has occurred mostly within a depth interval, you'll typically have porosity change across that depth interval. If porosity changes, permeability changes. So it actually changes water flow. So it's co-evolving the reactions and the water flow. And we're really trying to combine geochemistry, geophysics, and reactive transport modeling to understand this. I'm going to talk about the Susquehanna Shale Hills Critical Zone Observatory, which used to be funded as a CZO, and the CZOs are going away. This is a small watershed in central Pennsylvania. I'm going to talk first about that red dot, which is a borehole. We're going to look at a 1D profile. And I just wanted to make the point that this is one small place in Pennsylvania, but Jingu has just published a paper in GCA where we compared and saw lots of commonalities in other shale watersheds. And so I really think what we're seeing here is very generalizable, and that's important. So here's where we go from the 0.1 nanometer scale over here all the way to sort of like the tens of meters scales. These are all depletion profile plots, just like what I showed you. Let's start over here. This is that borehole at the red dot that I just showed you. This is depth again. And we're plotting sulfur, so 0% loss of sulfur, 100% loss of sulfur. Down here, you have all the sulfur that was in the original rock is still there. The sulfur in this rock is in pyrite, so the pyrite is there. Here's that reaction front. It's a narrow front, and then it's 100% gone. And you can sort of see some of these length scales here. Now, if you don't believe are those plots, when you look under SEM, this is a pyrite framboid from down here where we know there's sulfur. And then above that is the still what look like framboids, but they've been oxidized into iron oxide. So you can really see above and below the front. Now, the front is narrow, it's about 1 meter wide, but what we've discovered under the ridge is that if you go down here below that sort of real, sharp front, there are connected fractures down here where we see oxidation. So here's a piece from below the front along a connected fracture where you can see that there is actually, again, a depletion profile. So here's 100% pyrite, here's the reaction front, and now it's 100% gone. And look at the scale here. So we went from meters over here, tens of meters, to centimeters here. This is the reaction front. Then if you look at one of these grains where it's partially oxidized and come over here, here it is at the very smallest scale. It's a 200 nanometer scale bar, pyrite to iron oxide. And let's see if I go backwards, you'll be able to see this. Here is that depth profile. Here's that very, very narrow reaction front. My entire career, I wanted to have data like this. This is the first time where we have these reaction fronts at all three scales. We can now put them together, and I can't talk about this model, but we've been trying to, figure out the time scales across these so that we can come up with a model that takes you from one of these scales all the way to the bottom. What it looks like is summarized here, that oxygen is brought to depth of tens of meters in the groundwater and fractures. It diffuses inward into the matrix from fractures and oxidizes the pyrite abiotically. We think it's abiotic because the connected shale pores, which Jingu has measured, are very small, smaller than bacteria. So whereas the bacteria could be in the fractures, we see oxidation away from the fractures. That's got to be abiotic. And we can now look at the rates of these reactions, and we can make a model that's very consistent with what's observed in the laboratory and what's known about diffusion. All right, so that was the deepest reaction front, the pyrite oxidation. Most rocks are more than one mineral, of course. And so there's multiple reaction fronts. Here's that pyrite reaction front here, just shown schematically. The next one up is carbonate. Carbonate and pyrite dissolve closely. Chlorite is the main reacting mineral, and it weathers over a wide front. And at the very top up in the soil, you see that the illite weathers away. So here's that idea that these sharp fronts are like valves because there's porosity changes across there and we infer permeability changes. I think if you see a sharp reaction front like this, it often means that although the water is coming in from above, that there's a change in direction so that there is a lateral flow. And the same down here when you get to that deepest front. And then this wide front in the middle, this chlorite front, is showing you that indeed water is moving from the surface down. So I like to think of these things as reaction fronts. All right, now stay with me. That was under the ridge. Now I'm going to move under the valley and look at a borehole under the valley. And what we see, again, this is pyrite, 100% of parent pyrite. And then it reacts away, and then it's gone. So this reaction front for pyrite now under the valley is all of a sudden tens of meters in width. And you're remembering what I told you in the beginning, and you're already understanding what's going on here. And then we can put the other reaction fronts on here. Here's chlorite under the valley, no depletion, and then we lose it closer to the surface. But the front itself is actually deeper because this is the valley, so at an absolute scale, it's deeper. And then again, the illite weathers only at the top in the soil. So now I showed you some information from the ridge and then from the valley. Now we have 2D seismic. Seismic waves propagate as a function of things like the density and the porosity, so we can take a rock physics model and take seismic data and interpret it. And this is work now being done by Lisa Ma. She's talking this afternoon at 1:55. And this is the seismic transect from the valley to the ridge. This is the velocity of the P waves. And here's where the pyrite starts oxidizing under the valley. Here's where it starts oxidizing, or where the chlorite starts oxidizing. Here's where the pyrite and chlorite start oxidizing under the ridge. If you just really simplistically plot those together, this is starting to give you a picture of the landscape of oxidation and chlorite reaction across this transect. So remember, this pervasive pyrite oxidation, we know it starts here. So even though our seismic, we lose resolution down here. Then up here, we know the most pervasive pyrite oxidation starts here. But we know that below that, there are some of these connected fractures where there's halos of oxidation around them. And I showed you that picture. And lo and behold, look at the seismic is actually showing slower velocities. I didn't say this, but blue means fast, like the parent, and warm colors mean slow, where they're more porous. But you can sort of see there is some evidence for this geochemical reaction. So there's fractures down here that are oxidized and that we think we can see with the seismic. So I think what we're seeing here, and you can see it in the sort of gradations of color, is that there is flow in the subsurface in some of these connected fractures. So this is the conceptual model of the critical zone structure. Water comes in at the top. We actually know from a lot of measurements that almost 90% of the water goes out in that upper surface. We call this interflow. This is very common. And so I'm thinking of that sort of illite front up here, reaction front is like a valve. Some of the water infiltrates down to the regional groundwater table. And that infiltration is documented by that chlorite reaction front. And then here we start to see water that is, again, flowing now towards the valley. Now, this flow path is actually not a very long flow path, so there's still some oxygen. It has oxidized some of the chlorite and some of the pyrite, but there's still some oxygen. Some of it actually gets down into these connected pores. And then all these flow paths are getting focused under the valley and into the flow under the valley. But by the time they get over here, they're oxygen poor. So this is where the test from that, my second slide, you have a lot of flow and you have oxygen depleted, so you actually end up with a wider reaction front. And that's exactly what we see. So if we map these fronts, we're actually mapping fluid flow and something about the reactant concentrations. So it's very powerful. So the last thing I want to do now is show you the seismic transect up at the top of the watershed. So we were kind of looking at, down here, and now if we go to the top of the watershed, here's what the P wave velocities across that transect look like. This is a preliminary rendition that we're still working on. Here's the dense bedrock with fast seismic velocities. I forgot to mention on the previous slide, we documented that the chlorite reaction front is coincident with the 2,700 meter per second P wave velocity. So just mapping that on here just with straight lines. This is where chlorite oxidation begins. And we're now able to see it in 2D because of the seismic. And we still see this evidence that we think is fractures where there's some oxidation and kind of connected flow of oxygenated water. So we would love to model this. We can't, we can do it in 1D. We're starting to be able to do it in 2D, and we'd love to be able to go to 3D. This permeability architecture grows as reaction grows, and Li Li and her student Da-Cheng Zhao are working on this. And, it's a coevolution between the flow, the reaction, and the permeability changes that I think will tell us a lot about all sorts of processes and then also the structures in the subsurface. So this is what I want you to go home with. We're using geochemistry and geophysics to understand these subsurface landscapes. We can't imagine them yet, but I tried to give you a picture of what it looked like. The reaction fronts, I think, act like valves to reorient fluid flow. And we're only going to be able to do this if we can put all these kinds of data together. And I've given you 2 pictures to take. Thank you very much.
Thank you. A question for Sue. Yes.
Nice talk. I was wondering, you're thinking that permeability changes when you get these mineral reactions, or pyrite dissolution or dissolving or other things. But do you measure that, or are you assuming that?
Yeah, we're not measuring that. We have permeability measurements in some, from some plug flow tests and things like that. But no, we are assuming that. And what I'm noticing in other systems other than this one is that how often it does look like there is a change in direction of fluid flow at these reaction fronts. And the reaction fronts could actually cause the change in fluid flow, or it could be that the reaction front, kind of sits there because of some structural feature that was there in the first place. So I just think the reaction fronts can help us sort of start to conceptualize fluid flow, but it is more of a conceptual model and it hasn't been measured explicitly. In the permeability, you mean? Yeah, in the permeability. Well, but as you know, I'm sure, it's not just the change in porosity, it's the connectivity. And, as pyrite oxidizes and releases sulfuric acid and dissolves carbonate down there, we know it's starting to allow water to move through there. So really, it's all about connectivity, which, is a very difficult thing to measure and to interpret. But thanks.
Thanks, Sue. Matt? They are. You want to introduce? Oh, okay. All right, so thank you for that excellent opening talk. And next we're going to have Matt Winnick, who's going to be speaking about weathering regimes and lithium isotope signals of mineral dissolution and precipitation, a reactive transport perspective. Thanks, Matt. You're going to do the arrows here.
All right, well, thank you. So first, I just want to acknowledge my co-authors, Jenny Druin and Kate Maher. So I'm going to be talking today about some work to try to understand the mechanistic linkages between weathering regimes and lithium isotope signals measured in global streams and rivers. So just brief background, lithium isotopes are really powerful tracers of silicate weathering processes. This is enabled primarily by the fact that the light isotope, lithium-6, is preferentially taken up during secondary mineral precipitation relative to the heavy isotope lithium-7. And so as a result, lithium dissolved in streams tends to be isotopically offset from bedrock parent material, as shown in that diagram, tends to have higher delta 7 lithium values. And so lithium isotopes are directly tracing weathering congruency, or how much relative secondary mineral precipitation is happening. And so when weathering is congruent, when there's essentially no secondary mineral formation, we don't see these isotopic offsets between dissolved lodes and bedrock. And when weathering is incongruent, when there's a lot of this secondary mineral formation, these isotopic offsets are relatively large. And so today I'm going to be talking about how this weathering congruency is related to weathering intensity, which is just defined as the ratio of chemical weathering to total denudation. So our conceptions of this relationship have really been pioneered by some elegant work by Julien Boucher and Matthew Delanger that I'm just going to walk through briefly here. So let's see if I can move this mouse. Under low weathering intensity conditions, when physical erosion outpaces chemical weathering, we see regolith formation kind of confined to the top few centimeters of weathering profiles. As a result, soil and soil water residence time are thought to be relatively low, limiting the formation of clay minerals and accumulation, which leads to congruent weathering, and so relatively low delta 7 lithium in the dissolved load. Under moderate weathering intensity conditions, when physical erosion is comparable to chemical weathering, waters have time within the weathering zone to precipitate significant amounts of clays, leading to incongruent weathering and high delta 7 lithium values. And finally, when weathering intensity is high, when chemical denudation greatly outpaces physical erosion, we actually deplete regolith of primary minerals and transition to clay dissolution, resulting in this kind of characteristic parabolic relationship. I also just want to note that in Matthew Delanger's data from the Amazon, we also see this parabolic relationship between delta 7 lithium and lithium concentrations. And the thing I want to point out about this diagram is, in fact, the highest lithium concentrations are observed in these low weathering intensity environments. And what I'm going to argue a little bit today is that this observation may not be compatible with ideas that water residence time is really controlling these isotope systematics. Basically, if water residence times are short, we wouldn't expect to see the accumulation of lithium in solution. So to investigate this in a bit more detail, we've incorporated lithium isotope systematics into crunch flow reactive transport simulations of granitic weathering. For the purposes of this exercise, we're going to keep this really simple and idealized. And so we've made a bedrock mineral assemblage in which the dominant chemical weathering reaction is the dissolution of plagioclase and precipitation of halloysite, which is a clay precursor to kaolinite. We simulate lithium isotopes as two separate primary species, lithium-7 and lithium-6, and incorporate them in trace amounts into our plagioclase and halloysite minerals. And then to simulate isotopic fractionation during clay precipitation, we simulate two separate halloysite minerals, and we prescribe offset intrinsic rate constants. And what this does is induces kinetic fractionation during mineral formation, and we set these rate constants such that the kinetic fractionation factor results in an offset of about 18 per mil between dissolved lithium and clay formation, matching kind of global field studies. So I'm going to start by walking you through some results from some simple batch reactor experiments to get a sense of the overall dynamics. And then we're going to move into some one-dimensional weathering profile simulations in which we vary infiltrating flow rate and uplift and erosion rates to try to simulate a really broad range of different weathering intensities. So starting with our batch reactor simulations, we're going to start by looking at mineral dissolution and precipitation rates. So here, plagioclase dissolution is a negative rate here, is shown with the solid line, and halloysite precipitation is shown with this dashed line. So when these experiments start, dilute waters are far from equilibrium with our mineral assemblage, and so plagioclase dissolution rates are relatively fast, just right off the bat. In contrast, halloysite precipitation actually takes a while to kick in, roughly weeks to months of simulation time, as we have to actually build up enough aluminum and silica in solution to kind of oversaturate with respect to halloysite. And then you can see this jumps up, kind of kicks up pretty rapidly, and then both of these rates converge to zero as the system approaches a metastable equilibrium. In terms of weathering congruence, which I'm just calculating basically as the ratio of halloysite precipitation to plagioclase dissolution, because halloysite takes a while to kick in, we start with completely congruent weathering, which then weathering incongruence increases over the first weeks to months of simulations, kind of overshoots and then approaches a steady state value. And this directly controls our simulated lithium isotope systematics in the dissolved load. So with this initial congruent weathering, dissolved lithium isotopic composition resembles bedrock, in this case 5 per mil. And then as halloysite precipitation kicks in, these dissolved load values rapidly increase, kind of overshoot, and then approach some steady state, reflecting this full fractionation effect. So next, we're going to walk through some of these one-dimensional regolith simulations, looking at some similar kind of depth and mineralogic profiles that we're looking at. So starting with high weathering intensity simulations when chemical denudation outpaces physical erosion, we can see how the mineralogical profile evolves through time, going from these yellow lines to the dark blue lines. And so this is plagioclase mineral percentage or weight percentage on the left and halloysite weight percentage on the right. And you can see that basically plagioclase primary minerals are rapidly denuded from the profile. Halloysite precipitation accumulates throughout. And at some point within this kind of active weathering zone outlined in gray, we actually transition to clay dissolution. This is reflected by the end of the simulation in the lithium isotopic signatures of the dissolved load. And so what we see is that waters, solutes exiting this active weathering zone have really low delta 7 lithium values, reflecting this depleted clay dissolution, and low lithium concentrations as well, reflecting low clay solubility. Under moderate weathering intensity conditions, when chemical weathering is actually roughly equivalent to physical erosion, we see the development of these steady-state regolith profiles that are a little bit deeper with these characteristic reaction fronts. As a result of these longer reaction fronts, we can actually sustain active halloysite precipitation throughout this gray-shaded regolith profile, leading to incongruent weathering. And this results in relatively high delta 7 lithium values of the solutes exiting this regolith profile. You can see values of 15 to 20 per mil here, and relatively high lithium concentrations as well, reflecting the kind of approach to this metastable equilibrium. So far, both of these results have kind of matched the observations in theory. However, when we simulate low weathering intensity environments, rapid physical erosion kind of limits regolith formation to the top few centimeters of these profiles. You can kind of hardly see it here, but it's outlined in gray. And as a result of these really kind of thin veneer of regolith, water spends so little time in that zone that it actually limits the ability it limits clays from precipitating. And so we end up with congruent weathering within that thin regolith zone. And as a result, isotopic composition of the dissolved load of lithium is relatively low, again reflecting this congruent weathering. But also the lithium concentrations are extremely low. And again, with such short residence times, these weathering reactions can't actually accumulate lithium in solution. And so if we take a step back, I think what I've demonstrated is that with some really simple kind of idealized setups, we are able to capture this parabolic relationship between lithium isotopes and weathering intensity that are observed in global river data. However, we can't capture this parabolic relationship between lithium isotopes and lithium concentrations. And again, specifically, given a single kind of unchanging mineral assemblage, there's essentially no way that we can simulate these high lithium concentrations in low weathering intensity environments, assuming that this is completely dependent on water residence time in that regolith zone. And so what are some other kind of mechanistic ways that we can actually tie together these lithium isotope systematics and concentration systematics with weathering intensity? And I'm going to offer two potential hypotheses that I think we can kind of go out and test. These aren't necessarily meant to be exhaustive, but might provide some kind of good starting grounds. The first one is a potential role for contributions from geothermal waters to be playing a large role. And so geothermal waters, as shown by a number of studies, tend to have relatively high lithium concentrations and low isotopic composition of the dissolved lithium. And this is largely a result of high temperature reactions that actually limit clay precipitation. And so it seems consistent, we might expect that these geothermal waters would be contributing more lithium in rapidly uplifting systems. And so this might be a way, again, to link these low isotopic composition, high lithium concentration waters to low weathering intensity environments. I think the second option that I'm going to get into in a little bit more detail is a potential role for lithium-rich soluble minerals such as chlorite to actually modulate what chemical weathering reactions are dominating under different weathering intensity conditions. And so to demonstrate what this might look like, I've just incorporated a common chlorite mineral into our previous simulations, in this case clinochlor, given it really relatively high lithium concentrations and high solubility. So just really briefly, under both medium and high weathering intensity conditions, because it's so soluble, these chlorite minerals are rapidly denuding from the regolith profiles. And basically the result of this is that these medium and high weathering intensity simulations just match our previous simulations. Chlorite is not able to contribute to lithium fluxes because it's been denuded from these profiles. Only when weathering intensities are low, when uplift and erosion rates are essentially high enough, can we actually maintain steady state dissolution of these highly soluble chlorite minerals within this thin regolith zone. And as a result of their high concentrations, which actually overwhelm the ability of clay precipitation to uptake enough clay to cause these isotopic offsets, we observe simultaneously low lithium isotope composition and relatively high lithium concentrations. And so taking another step back, I'm just comparing these model results now with our chlorite incorporation to the data from Matthew Dellinger's paper. And you can see that using this kind of setup, we are able to capture this kind of dual parabolic relationship between lithium isotopes and then weathering intensity and lithium concentrations. And essentially, again, what's happening here is that under low weathering intensity, chlorite dissolution dominates. Under medium weathering intensity, plagioclase dissolution dominates. And under high weathering intensity, clay dissolution dominates. So again, these aren't necessarily meant to be exhaustive, but I think they provide two options that we can kind of mechanistically link these lithium isotope systematics to weathering regimes and hopefully provide us with kind of better constraints on what lithium isotope proxies are actually representing when we go back and try to reconstruct the past. So thank you all.
Just probably one quick question while we switch speakers.
How do you control what the equilibrium constant is for the precipitating lithium-bearing end members if you just do the rings?
Yeah, so they have the same equilibrium constants in this result. Like if you differ the equilibrium constants, we actually get basically varying isotopic composition of the clay minerals throughout. I'm happy to show you some of the code that we've kind of played around with this, but we haven't been able to get very stable simulation results. Yep.
Thank you.
Yep.
Thanks, Matt.
Okay. Next, we have Eric Sonnethal from Berkeley Lab talking about reactive transport modeling of redox-driven reactions and in the context of hydraulic stimulation.
Thank you. Such a big room. So you should have brought our 101 geology class.
This is,
This is mine.
yeah.
I'd like to present some reactive transport modeling study. It's a large group working underground at the Homestake mine, studying fracture propagation. In order to learn more about how to develop enhanced geothermal systems. So I'll give a little bit of a study that I did earlier this year. So What we know is that hydromechanical processes primarily control fracture propagation in enhanced geothermal systems. You inject water and you either fracture the rock through shear failure or tensile failure, not too different from hydraulic fracturing in unconventional oil reservoirs, but typically more driven by shear failure events. So as part of the US DOE geothermal program, experiments were performed underground in the Homestake mine at the 4,850-foot level, so almost a mile underground. And it involved injecting water into the carbonate-rich metasediments to generate hydrofractures and to study them. And in particular, the water that was injected, this mine water, was more dilute than the existing pore water, and since it had been sitting around, it's quite oxygenated. So after they created some hydrofractures, they continued to pump water at basically continuous rates, but there was an unexpected rise in injection pressure. So the fractures basically started closing up, and they couldn't maintain those conduits in the fractures that they had generated. And several experiments were done, and it kept showing this kind of behavior. And at the same time, there were many measurements done of pressure, temperature, microseismicity, really nice ERT imaging, and tracer testing. The hydromechanical models that were done basically looked at, well, what can cause this? Well, one pretty simple aspect is if you inject water, create a fracture, eventually that pressure starts to diffuse into the surrounding matrix around the fracture, and that kind of swells the fracture up, which ends up closing it down. So it's basically a poroelastic effect. However, there were some indications that geochemical and biogeochemical effects were going on because they injected different waters, they added biocides, and things changed. And it seemed like those changes due to poroelasticity would probably be very small given the very low porosity of that metamorphic rock. So then it was like, okay, find a geochemist. So anyway, that's when I started doing a few experiments to look at what geochemical effects could there be. Well, what's our motivation for doing all this modeling? Because enhanced geothermal systems really could provide a lot of energy because of having a lot of hot rock, but not very much water and not very much permeability. So to do modeling, we want to evaluate the effectiveness of stimulation. And we can use geochemical and isotopic systems to look at many processes that you can't really understand just by looking at pressure, temperature, seismicity, particularly mixing, water-rock interaction, degassing, et cetera. And then you can look at various other things such as composition of injection production fluids, evaluate effects on permeability. So this kind of work at the large scale fits in perfectly with studying these effects at the mine scale, which is really on the order of tens of meters or meters. So not to talk too much about modeling, but the basic approach is to solve a flow equation, multi-phase flow. Then you solve maybe in a mechanics equation. And I'm not going to talk about mechanics here. I'm just going to look at the chemical effects because we're just going to assume that this fracture has been created. We can look at fracture generation, but that's pretty much a very fast process. And so we know really we had this fracture happen. They happen in minutes or seconds. And then we can transport all the species advectively and diffusively. Then we react minerals, aqueous species, gases, so forth. And then all these processes coupled to produce porosity changes. And then with various laws that you might use, then you create permeability changes. So of course, all these have many uncertainties, but this is why you run a lot of simulations and you use a lot of alternative data to try to constrain the models. So this is all embedded in this kind of tough React, 2 ReactMech codes that we've been developing over a couple of decades, several decades now. What's the site, Homestake Mine, the CoLab facility in South Dakota? So we're at about 4,850 below the surface, and we're in a, is there a, okay. The site is right here in this Poor Man Formation. There's also this dike swarm, and we're not far from the Yates Formation. Most of the mining is actually in the Homestake Formation, which is kind of off the sheet here, although there's a fair amount of sulfides also in the Poor Man. And what does this rock look like? Well, the Homestake, this is the real mining horizon. But the Poor Man isn't too different. It's a lot of carbonate-rich metasediments, pyrrhotite, there's arsenopyrite. There's a lot of minerals other than these, but dominantly biotite, quartz, chlorite, a range of carbonates. And as far as sulfides, the main ones are pyrite and pyrrhotite. So, well, what's our modeling approach? So we want to build we want to look at processes happening within a fracture and in the adjoining matrix. So we're going to build a 3D discrete fracture reactive transport model. And we're going to assume an initial permeable hydrofracture. And then we're going to add mineral dissolution precipitation, equilibrium kinetics, porosity permeability changes, temperature changes, and pressure evolution. And one aspect that usually people don't look at is that because sulfide oxidation is really enthalpic, so it can create a lot of heat if you have enough oxygen. So in this case, it's not clear how saturated that rock really is, because we know that in mines you can create a lot of heat because of this. So we added to the code heats of reaction a couple of years ago, and this was kind of a way to use it for a problem. This is all coupled in for the full geochemical process. And we also looked at flow pathways, we looked at the inlet pressure changes, and we also looked at electrical conductivity changes of the fluid. I'd thought about that for a long time, and then Pat said, oh, they have some great data, here's some papers, and we put it in the code, and it's actually pretty useful for mapping out compositional changes. So what does the model look like? So this 3D model, there's a thin fracture here, and it's actually at about 2 millimeters, but with some rock in it. So it's about a 500 micron fracture. So half a millimeter, fairly permeable fracture. And then it's surrounded by matrix and very finely gridded all around. And so this is about the scale of, between drill holes, about 10 meters or so. Permeability, about 10 to the minus 15 for the rock matrix of the Poor Man, and pretty high for the fracture, 10 to the minus 9 meters squared. These are the porosities and apertures, thermal conductivities, heat capacities, tortuosity. So basically we have about 30,000 elements, and we're going to look at, injecting water into this fracture over time at the rates that they injected at, which is about 0.01 kilograms per second. And there's a little bit of a temperature change. The water is about 15 degrees centigrade. The rock is about 30 or 32 degrees centigrade. So what are the things that we might expect to see in these cases? Well, there's a whole series of oxidation reactions, starting with, say, pyrrhotite oxidation, going from sulfide to sulfate. And basically, through all these reactions, most of them generate a lot of hydrogen ions, so decreasing pH. And going through pyrrhotite oxidation, then we can form things like ferrihydrite, goethite, so forth, iron hydroxides. And then finally, with Fe3 plus and sulfate, we can form some of these kind of odd mine minerals like schwertmanite and so forth. So these oxysulfates, hydroxides. So these are the kind of reactions we have driving these pH changes. And then these pH changes affect carbonates and silicates in the mineral. And for example, this is just a picture of some gypsum that you see forming out of one of these fractures, where you know that oxygenated mine water has been reacting with sulfides. So the geochemical system, it's pretty complicated because you have this kind of almost a banded iron formation of carbonates, chlorite, multiple end members of chlorite and biotite, amphiboles, sulfides. So these are basically the primary minerals. Then you have to consider all the potential secondary minerals. And there are many that could form, and you don't want to leave out any. So basically, anything that could form could be any of these primary minerals, plus any of these secondary minerals. Some of them are treated as kinetic phases, and some of them are treated because they would precipitate very rapidly as equilibrium phases. So the blue are in equilibrium phases. So primarily things like the sulfates, fluorite, and then these iron hydroxides, schwertmanite. And the main issue here is this difference of the mine water. pH is about the same, but the main thing is that it's more dilute and it's been sitting and interacting with the oxygen. And then the water that's been found in the mine itself is, of course, much more reducing and not nearly as dilute. So there's about a factor of 20 in chloride. So different in terms of electrical conductivity, and this is obviously much more oxygenated. So we just run some simulations, because it's nice to just run them and see what happens to have as much possibility to get different behavior. And we did get a lot of very interesting behavior in this simulation. So for example, you can see the temperature here. It's about 15 and about 30 degrees here. And you see the pH after 2 days starting to get quite a bit of variation. You get a very low pH band up in here, somewhat higher here. It's starting out in the 8s or so. And if you look at ferrihydrite's actually forming out at this front. Calcite is forming in this region, but it's dissolving out at this lower pH region. So you're getting this front of differing bands of mineralization happening in the plane of the fracture. And just as you're dissolving arsenopyrite, you can see where the arsenic is growing, and it's kind of being pushed along with this front as well. And then other things, the porosity. You know, after 2 days, we don't get a lot of change, but we're starting to get like a few % change in porosity out in this band here, decrease in porosity, and small increases out in this front where it's more acidic and you're dissolving. And you can see this jumping up here. That's calcite precipitation in this region, and some of the other minerals in lesser abundances. And one thing you see with the flux, these are the flow vectors, the flux ratio of X to Y, it actually increases, which means that you're basically starting to plug around the inlet and you're pushing the water out to the sides. And so after 6 days, now we start seeing more of this schwertmanite forming really near the inlet. And calcite, we're getting a nice big band out further of precipitation. We're still dissolving it out at the front, and the porosity change keeps increasing. You keep dropping porosity right near the inlet, and the permeability ratio is down to about 80% of the original in this same region. And then after 10 days, we start getting more calcite. So we still keep seeing calcite out here. We're dissolving it near the inlet. The porosity keeps dropping. That's about a 4% drop in porosity. Now we have about a 50% drop in permeability right near that inlet. And you can see this band of schwertmanite, it's actually pretty strong, about 4%. So we're basically plugging the inlet, but we're also forming calcite further out. So actually, when they pulled out some of the packers several meters away, they pulled out these grungy packers, and you'd think there'd be other minerals here, but mostly what they were able to find by XRD is just calcite. It doesn't look like calcite, but it's mostly calcite. But this is further away, so we really don't know what minerals are forming right near the inlet until they pull out some of those fractures. But certainly there has to be some of these iron hydroxides. We don't know if there's really schwertmanite at all, but this is consistent with dissolving calcite through acidity and then precipitating it out further. 2 more slides. So, whoops. So then we looked at the electrical conductivity is a really good way of looking at how the fluid reactions are moving through the system. So we're injecting. The electrical conductivity injection fluid is lower because of the lower salinity, also because of the lower temperature. But it's also, you can see it's diffusing into the rock matrix. And the rock matrix is reacting. It's starting to get, this reaction front moving into the system. And then you have the front that's moving down the fracture. So out here, it's pretty much just confined to the fracture, but out here, it's already migrated in. And if you look at the pressure increase at the inlet, which is basically what you can measure in these sites, not a whole lot else at the inlet, that the pressure will non-linearly just keeps increasing because of this drop in permeability. A linear increase in pressure would just be like this. So this is probably a lot more than you would get through just the simple poor elastic effect, and it would keep continuing if we were to run this longer and longer. And it makes sense. I mean, these are the things you see in mines with oxygenated water. So in summary, the injection-induced reactions were pretty obvious. Injecting oxygenated mine water would be dominated by pyrrhotite oxidation, and then a bunch of iron hydroxides, maybe schwertmanite, would be precipitated very close to that region, would suck up the oxygen, and then start precipitating out and dropping the permeability. Calcite does start to form out further, which you observe. And it's a pretty strong effect after just 10 days at a very small injection rate of about only 0.01 kilograms per second. So this reaction front was very nicely shown through ERT measurements. I don't have any of those yet, but Tim Johnson has shown some really nice imaging of that, but it looks pretty similar to what we observed. Basically, you can map out the flow through the fractures and maybe into the rock matrix. It's not clear that we have that kind of resolution. The thermal effects of sulfide oxidation tended to be only a few tenths of a degree. And the reason for that is we don't have any oxygen really getting pulled into the walls. In actuality, there may be some unsaturated regions. So, you know, in our model, we assumed it was fully saturated. The only oxygen there is what you're actually injecting in. So that gets consumed pretty quickly, and the heat effects are just limited by that amount of oxygen. If there's any convection with air in the tunnel, then you can really generate a lot of heat, like you do in a mine pile. And then, you know, we did observe calcite precipitation. You know, all these reactions can generate microbiological activity, and that probably is happening. That would be kind of the next step in modeling, would be to add some of those. So in conclusion, you know, whoops, what happened there? Kind of lost their slide. In conclusion, you know, we have a lot of people looking at mechanics, we have a lot of people looking at geochemistry, and really a lot of these systems, you really can't separate them, because almost any time you inject water into rock, it's going to be in disequilibrium. And some of those reactions may not be very fast, but sometimes if you're injecting into carbonate-rich, sulfide-rich, even rocks that don't seem very different, you will always get geochemical effects. On the other hand, you know, permeability is always being changed through mechanical effects. So in the end, you really have to consider all of these to really understand how flow, reaction, and permeability changes happen in the subsurface. Thank you.
Thanks. I don't think we have time for questions at this point, but please make sure to talk to Eric afterwards if you have any questions. Thank you. And,
Go ahead and introduce her.
and next, we will have Anna Harrison to talk about carbon mineralization.
All right, good morning. So thank you to the conveners, first of all, for giving me the opportunity to speak today. And so one of the things we study are carbon mineralization reactions. So these are naturally occurring processes that have helped to regulate atmospheric CO2 concentrations on the global scale over geologic time. They can also be harnessed and accelerated to provide offsets of anthropogenic CO2 emissions, and are therefore a promising part of climate mitigation strategies. But to effectively use these reactions to capture and store CO2, and to better understand their role in longer-term carbon cycling, we need to identify the mechanisms and processes that influence the rates of these reactions and how they progress. So overall, carbon mineralization involves three main steps. So it's the dissolution of alkaline earth metal-bearing silicate or hydroxide minerals, which releases cations like magnesium to solution. These cations then react with dissolved CO2 to form carbonate minerals that act then as a solid sink for CO2 that's stable over essentially geologic time. Now, notably, water is required for all of these steps. So it facilitates and enhances dissolution of minerals. The dissolution and hydration of CO2 is necessary to form carbonate minerals, and some of our carbonate minerals are actually incorporating water into their crystal structures. So we expect then that the availability and distribution of water is going to be a key control on the rates of these reactions and the degree to which they can progress. We expect water-limited reactivity to be important in a number of environments, but today we're just going to focus on these carbon mineralizing reactions in the context of engineered CO2 storage, so which is relevant for geologic CO2 sequestration, where CO2 is injected into the subsurface, as well as near-surface sequestration measures, where, for example, we react magnesium-rich mine tailings with CO2. And so one of the questions we have here then is, does water availability influence actual reaction rates, or is it simply determining whether or not reactions can occur? And so one of the ways we can get at this is by looking at results of some column experiments we conducted. These were meter-scale columns that were filled with 10 weight % brucite, which is a magnesium hydroxide phase that reacts readily with CO2 to form carbonate minerals. The rest of the column was 90 weight % quartz, which is effectively unreactive in these systems. It's there more to make up the bulk of the porous medium. We varied the bulk water saturation between experiments, and there's also a gradient with depth, so more water at the base, less water near the top. And we supplied a CO2-rich gas at 10% CO2 that flowed in through the base of the columns and exited at the top. We could track the reaction by having these CO2 sensors along the flow path, which monitored the removal of CO2 from the gas phase into the mineral phase. And we could also excavate these columns afterwards and observe where minerals had formed and how much carbonate had formed with depth. And so what we observed is similar to what we expected. So essentially the amount of carbonate precipitation was strongly dependent on the distribution and availability of water. So for example, as shown here at the base of our columns where we have high water saturation, we observed extensive carbonate precipitation occurring throughout the water-filled pore space, shown in this image on the lower right, where carbonate has been false-colored in burgundy. In contrast, in the upper dry regions of our column, shown in the upper right, carbonate was only observed to form as these very thin, flaky rinds, about 4 microns thick, surrounding both brucite and quartz grains. And by excavating our columns at the end of the experiment, we could correlate the amount of reaction with the water saturation with depth. And so that's what's shown here, where we have the amount of CO2 sequestered on the y-axis, so essentially the amount of carbonate minerals formed, versus water saturation on the x, where we typically observed a reduced amount of reaction at low water saturation that starts to increase as water saturation increases and declines again at very high water saturation. Now, the reason for this decline at high water saturation is essentially a transport limitation, not a reaction limitation. You get increased development of preferential flow paths at high water saturation, so a lot of the porous media is just bypassed by that CO2. In contrast, the reason for lower extent of reaction at low water saturation is less clear. And so what we did here is we applied a reactive transport model, Min3P, to simulate our experimental conditions, with the idea being that any difference between our model and our experiments informs us as to the processes that might be missing from our model under these low water conditions. And so the results of this modeling are shown here in terms of CO2 breakthrough curves, with CO2 breakthrough in the gas phase on the y-axis versus time in hours on the x, with our experimental data shown by the solid lines and our model data by the dashed lines. What we can see is at the base of our columns, where we have high water saturation, about 90%, shown in black, we get pretty good agreement between our model and the experiment. Similarly, in the middle of our column, about 20% saturation, shown in red, pretty good agreement. But in the upper dry regions of our column, shown in green, we start to observe the biggest mismatch between our experiment and our model. Namely, our model is over-predicting the amount of reaction that has occurred. Now, there are a number of potential explanations for a reduced amount of reaction at low water saturation. For example, we may have an effectively reduced reactive capacity, so a lower amount of total reaction possible, as we just don't have enough water to facilitate these reactions. We may also have an effectively reduced reactive surface area, as some grains may be less exposed to the reactive fluid than others. This would reduce our effective surface area and thus our bulk or effective reaction rate. And so we incorporated these two ideas into conceptual models that were implemented in Min3P. So one of these we call the dry pore model, which divides our porous medium into dry unreactive pores and wet reactive pores, the proportion of which depends on the water saturation. So in this case, we've reduced both the reactive capacity and the reactive surface area, as we've essentially removed part of the porous medium from being able to react. In contrast, we have what we call the damp pore model, which assumes water is homogeneously distributed across all mineral surfaces. So the surface area is maintained, and therefore the reaction rate should be maintained, but still the amount of reaction possible is limited. And so we applied these models into Min3P with results shown here. The dry pore model on the left-hand side does a bad job of reproducing our experimental data. The damp pore model on the right-hand side does a better job of reproducing our experimental data. And so what this suggests is that the reaction rates are not different in these low water environments compared to the water-rich regions. Rather, it's just the amount of reaction that's limited. So we can't react as much and we don't have as much water available. It sounds like sort of a subtle difference, but it's actually a pretty big difference in how we would approach modeling these systems. And you get quite a different result if you, for example, try and simulate a reduced amount of reaction by lowering your surface area, which is often what's done, but it would not work well in this case. And that's important if we're trying to model CO2 storage security, for example. All right, so these columns suggested that we didn't need too much water to have a wetted surface area available for reaction, but we wanted to delve into this a little bit further and better define, well, what is a wetted surface area? How much water do you really need for these reactions to occur? And so to do that, we conducted a series of experiments where we grew magnesium carbonate minerals under extremely dry conditions. And so by extremely dry, I mean we had no visible liquid water available. The only water available for reaction is humidity in the atmosphere. And so it's known if you expose a mineral surface to a humid air, you will develop an adsorbed water film at its surface, the thickness of which depends in part on the relative humidity. And that adsorbed water film may be enough to facilitate reactions. And so what we did is we took our mineral brucite again, we exposed it to different levels of humidity, which we controlled using saturated salt solutions, ranging from 29 to 100% humidity. And we exposed it to either lab air or 100% CO2 and tracked the reaction over time. And so what we observed in these experiments was, first of all, that both dissolution and precipitation could be facilitated just in these adsorbed water films under all humidity conditions. So we didn't need liquid water contact to have a wetted surface area. We did, however, find that the extent of reaction, again, was extremely sensitive to the relative humidity. So for example, shown here, we're looking at brucite surfaces reacted with atmospheric CO2 for 70 days as a function of humidity, with increasing humidity from upper left to lower right, so going from 29% to 53% to 75 to 100%. And these little flaky things you observe at the surface, that's our magnesium carbonate minerals identified with infrared spectroscopy. And so you notice these are present in all humidity conditions, but there's very little overall reaction at humidity less than 100%. There's very little difference between these humidity conditions, less than 100%, and we didn't observe continued reaction throughout the experiment, which was over a year long. In contrast, our 100% humidity experiment, shown in the lower right, we observed these very large crystalline magnesium carbonate minerals forming that continue to grow throughout the experimental duration. So to summarize these observations here, these are our brucite surfaces reacted with atmospheric CO2 for 378 days, which is the end of the experiment, where again we apparently have this threshold effect where at low humidity conditions we see little overall reaction, little difference between humidity, and little extensive continued carbonate growth. This suggests that we have a sort of threshold value of relative humidity, perhaps related to a threshold water film thickness that's required to facilitate more extensive reaction, potentially higher rates of reaction. But one of the things we wanted to get out of these experiments, ideally, was reaction rates as a function of water availability, so as a function of humidity in this case, with the ultimate goal that we might incorporate these into our reactive transport models to allow us to better simulate these conditions where we have low water. And so that's what's shown here, where we have the brucite conversion rate, so brucite going to magnesium carbonate on the y-axis versus partial pressure of water on the x, where again we observe this thresholding effect. So our atmospheric CO2 experiments are shown by the black diamonds, and pure CO2 by the white squares. And in both cases, we see at below this threshold low overall rates of reaction that are essentially independent of humidity. When we reach this threshold, our reaction rates increase. And notably, so the two blue points here are the same reactions but occurring in water unlimited conditions. So in batch reactors where we have a small amount of solid, a large amount of fluid. And what you notice is, particularly for the atmospheric CO2 experiments, our rates at 100% humidity are not really that far off what we observe in water unlimited conditions. Granted, there's uncertainty with the way we can calculate these rates. But nevertheless, we have rates that are not far off water unlimited conditions. And so ideally what we'd like to do is better constrain these reaction rates, particularly above this threshold, and hopefully incorporate these more mechanistically into our reactive transport models. And so in summary then of these observations and what they mean for CO2 storage, it appears that we may have a sort of ideal water content that will maximize the amount of CO2 stored. And so for example, it's expressed here in terms of the extent of reaction on the y-axis versus water saturation on the x, with an ideal water content shaded in gray. So for this particular reaction, between about 35 and 60%. So we have enough water that reactions can progress till they finish, but not so much water that we end up with these preferential flow effects. And this is going to be relevant for gas-driven reactions in general. And so in summary then, what we've observed is that carbon mineralization reactions are strongly impacted by water availability, but it's more an impact on the amount of reaction that can occur versus the rate of reaction. And this is an important distinction for how we can choose to model these systems. But ultimately, we're still missing a bit of a mechanistic approach here, and that's what we'd like to move towards to better incorporate water limitations in our reactive transport models, both for CO2, modeling CO2 storage security, but for modeling in general in these water unsaturated systems. Thank you.
We have time for one or two quick questions.
Do you know which magnesium carbonate you have?
Good question. It's most likely dippingite. So we identified them with infrared spectroscopy, but the spectra for dippingite and hydromagnesite are almost identical. So we don't know for sure whether it's one or the other, but usually under these low temperature conditions, it's more likely to be dippingite, and based on the morphology.
Thank you.
Okay, so next up, we're very excited to have Yixin Wu, who's going to be presenting on calcite reaction dynamics from low-frequency impedance spectroscopy across scales.
Okay, so I actually tweaked the title a little bit, but it's pretty much the same. Sorry, it's last-minute change. So this is actually the work that's conducted at Lawrence Berkeley Lab and also in collaboration with the ULIC group. And we kind of try to, to apply a ultra-low frequency impedance spectroscopy to understand calcite electrolyte interface. Looking at how the session is going, I think it seems like it's going downscale. I think this is a technology that sits in the middle, but I think I want to really show today how this actually can link microscopic observations on the mineral interface, but also something you can observe actually at field scales. So the funding for this work is supported by DOE BES, Basic Energy Science Program, and also BER, Biological Environmental Research, and the European Union funding through their 2020 program. And I'm going to start by introduce a little bit of the background in electromagnetic sensing, if you don't have you're not working in the field, and how the ultra-low frequency impedance spectroscopy is used, and the signals that are associated with calcite precipitation, and how it actually can be used to look at the actual transition of the system in and out of equilibrium by looking at the dynamic change of the impedance signals, and how this actually links with the microscopic surface charge structure, and actually how that actually can be observed at a field scale, and follow up by a quick summary. So EM-based sensing and characterization. This basically shows a nice kind of a cartoon of the different frequency range people are using to characterize minerals. EM wave is, I think this is pretty much most of the modern characterization technology are based on EM waves at different frequencies, different energy levels. For example, if you look at the infrared to UV range, you look at for example, UV spectroscopy, infrared spectroscopy, Raman, and also fiber optic sensing. All these are actually using these higher frequency EM wave, basically photon interaction with matters. And we actually go down the frequency range. You are actually talking about a lot of the geophysical approach that we heard some today. Ground penetrating radar, EM tools, ERT, and AMR. And what I'm going to focus on today is this ultra low frequency that are below 10,000 hertz all the way down to millihertz range. So at this frequency range, you're actually really looking at the interaction of the energy EM wave with the ions in the solution that actually can be linked to a lot of the very interesting interfacial processes. So again, looking at the low frequency impedance wave, what you're really are looking at are actually the charge transportation behavior in porous media. When you actually apply a low frequency energy, you actually have charge that going through the interconnected pores, and there are also those actually going at the mineral interface that actually are linked with the charge behavior in the electrical double layer. And when actually you have mineral precipitation or dissolution reactions, you actually modify this electrical double layer property, which actually give you a change in the signal. So basically, there again a link to the interfacial structure. And when you actually apply a low frequency EM wave, you basically perturb this interface. That actually the charge in the electrical double layer actually reacts to this low frequency energy that actually can be used as a probing tool to look at this properties at the interface. So typically, people actually treat the interfacial behavior as a kind of an analog circuit model where you have both a conduction component and also a capacitive component that relate to the electrical double layer. And this can be conducted and or measured in both time domain or frequency domain. In time domain, you're basically looking at the charging behavior of the interface. When you actually turn off the electrical the power, you don't have an immediate drop. You actually have this decay of the electrical conductivity. And when you look at the frequency domain, you have this basically, you scan the system through a range of frequency. You have this frequency-dependent conductivity. You also have a phase or imaginary conductivity behavior that shows this kind of dispersive behavior. And the magnitude and the location of these imaginary component is characteristic of the electrical properties. So talking specifically about calcite, and we actually are really using this technology to look at the behavior at the interface, and particularly the stern layer that's close to the mineral interface. And again, this is just a kind of a simple structure of the electrical double layer. And a lot of the technology existing actually, for example, looking at the charge data potential at the shear plane, which kind of more or less overlap with the zone of the perturbation we can do with the low frequency method. So calcite is actually a very complex and dynamic system, and there are a lot of very large uncertainties, for example, in terms of what is really the surface potential and what is the control on that, whether it's a pH or PCA. And again, this is just a figure showing the kind of a range of data you have in the literature. There's some actually new study that actually show, for example, what's actually controlling the interfacial charge properties, not pH, it's actually PCA. And for calcite, the charge determining ion is calcium and carbonate ions. This is a nice illustration of how the zeta potential is independent pH, but actually rather controlled by PCA. So there's actually a very strong connection between surface charge and the forces on the surface that have a strong impact on how calcite form and the stability of the calcite mineral, and also how that calcite interacts with host rock. And a lot of these existing studies actually look at equilibrium conditions, and they often emphasize equilibrium conditions during the studies. And this is actually whether the system at equilibrium has been considered as a main reason for the large range of results in the literature. But actually, many natural and also engineered systems actually at disequilibrium, and how actually the surface charge property under disequilibrium look like, and how actually they actually interact with the host rock is very important for their applications. And there are actually very limited tools available to understand the system under disequilibrium conditions. So basically, the question we try to answer with the low frequency impedance spectroscopy is what is actually the calcite surface charge look like under disequilibrium conditions, which is very transient, very hard to study because it's not stable. So basically, we started with some very simple experiment a while ago where we look at under this equilibrium condition where you actually just precipitate calcite by combining calcium and carbonate in an abiotic condition. This is an experiment conducted in glass bead. You can actually see as time goes by, we have this very nice consistent increase of the impedance. This is actually the imaginary component over time, not only in the magnitude, but also shift of the peak from the higher to lower frequency. This again is I'll talk about the link to the surface property later. And we actually do this in a biotic condition. This is a microbial-induced calcite precipitation that has very different mineral morphology. You do see this very similar behavior also, again, increase of the magnitude and also shift of the peak from higher to lower frequency over time. So this basically shows a very high signal from the disequilibrium condition during calcite precipitation. What's interesting actually is we observed when you actually turn off the calcium and carbonate injection, which basically allow the system to fall back to equilibrium from this disequilibrium condition, you have a very rapid decrease of the signal and also shifting of the peak from low to high. And within a few hours, and if you actually start the injection again, the signal quickly go back again. So you actually, this kind of a back and forth can be controlled to a point. It's really repeatable. And this is actually a repeated observation not only in our data a while ago, but also a recent experiment done at Germany using different media, different setups. So this actually demonstrates the repeatability of this observation. So just to summarize what we actually are thinking, what's really happening is this cartoon where actually when you actually look at the time versus the signal we're respecting, when you actually transition into the equilibrium, you have this increase of the signal. When you fall back to the equilibrium, you have this decrease. And basically, this is the kind of pattern that we're observing in the experiment, which basically suggests the actual signal we're observing are actually not related to the actual presence of calcite, but rather its status, whether it's actually under equilibrium or equilibrium condition. So this is very interesting and about why. So actually, if we look at, again, going back to the calcite surface charge structure, we look at the electro double layer with the stain layer, diffuse layer, and the free electrolyte, and how the potential profile looks like. And I think what we think is happening is when you actually under equilibrium conditions, the electro double layer is more or less a static condition. People actually don't typically consider that as a very dynamic, although that's not really true. But under this condition, you have a stern layer that's actually has reduced ion mobility. This is where we are getting most of the response from. But actually, under the disequilibrium or particularly supersaturation condition, you have the active growth of the mineral. So there's actually the ions that are rushing to the surface to form crystals. You actually likely have this. What we are thinking is the extended stern layer. Basically, you have a much thicker stern layer and potentially much higher charge density at this interface. This actually is linked to the signal we think that we're observing. So in terms of the saturation index of the system, you looking at the mineral interface and going away from the interface, and this is a nanometer scale, you can actually see under equilibrium condition, the saturation index is pretty much 0, but under supersaturation, you have this profile that are related to the precipitation process of the calcite. In terms of ion mobility, you can actually compare these two situations. Under equilibrium condition, you have a shorter distance where the mobility is decreased because of the bonding to the surface. But under supersaturation condition, because of this growth of the mineral, you likely have this extended stern layer thickness and also reduced mobility because of the higher concentration of ions that are giving you this heightened impedance response. So basically, in terms of the electrical potential, we actually can compare conceptually the equilibrium condition versus supersaturation condition. We have basically this heightened profile where for example, the deposition on the shear plane is much enhanced. And again, there are actually data in the literature that shows when you're actually moving away from equilibrium versus moving toward equilibrium, you have this actually there's a potential change that are actually theoretically calculated. So basically, again, to summarize what we're observing here in this cartoon, this actually basically shows the comparison between equilibrium and the supersaturation condition, where you have this shift of the stern layer structure going either from equilibrium to supersaturation or the other way around, actually generated this behavior that are linked to the surface interfacial properties. And this actually is observed in the field. This actually shown data from Rifle, Colorado, where you have the baseline condition, you have calcite precipitation in process, and you have this approaching equilibrium. You can actually see in this block showing the signal that actually related to the calcite. But when the calcite precipitation stopped, you actually the signal is disappearing. So this actually is a signal that you can observe in the field. Just to quickly summarize, this is basically the frequency, the data we're observing is linked to the interfacial property. The calcite surface charge play a big role in controlling the kinetics of calcite precipitation in interaction with host rocks. And the low frequency impedance give us a great tool to select interfacial charge and how the system transition in and out of equilibrium can actually result in a large impedance signal change. And the data from the field suggests that this is actually the tool that's viable for large-scale applications under realistic conditions. And we're actually working on trying to come up with a mechanical model to understand how this interaction is happening. And with that, I'll stop. Thank you.
Great, perfect timing. We have time for one question as we're switching over. Eric.
Yeah, so that's right. Magnesium is considered one of the potential PDIs for the calcite system. We didn't run experiment in our study, but there are existing data that shows if you actually add magnesium into the system, they actually behave very similar to calcium. So they will have an effect on the surface charge and the signal potentially. Yeah.
Thank you.
Thank you.
Good. Next up, we have Sophie Roman, who's going to be speaking about experimental microfluidics to improve mechanistic understanding of multiphase and reactive flow processes in Earth systems. Thanks, Sophie.
So good morning. So first I want to thank the conveners to give me the opportunity to talk here today. So we're interested in looking at mineral-water interaction because there are important processes in mineral mining, geological sequestration of CO2, the exploitation of geothermal heat or enhanced oil recovery. One example is the injection and sequestration of CO2 in deep saline aquifers, because in these processes, pore-scale processes will influence macro-scale behavior considerably. And for example, when we have drainage and imbibition mechanisms, when the CO2 will displace the water that is in place, we can have interface mass transfers at the interface between CO2 and the brine. We can have a decrease of the pH and transport of acids at the mineral surface with a reaction of dissolution or precipitations. And this reaction can lead to change in the pore space geometry and influence transport properties. So some of the challenges that we face are how these hydrogeochemical dynamics at the pore scale will influence microscale behavior, and how can we evaluate the consequences of mineral precipitation and dissolution on the evolution of the macroscopic transport properties of the media, like porosity, permeability of reactive surface area. So for that, there is a need of experimental data at the pore scale. And so this is why we are using micromodels. So typically micromodels, we have a pattern that is etched on the surface. So either silicon surface or a PDMS surface, and then this pattern is covered by a transparent plate. And so these micromodels, they allow to have a direct visualization of the flow mechanisms and reaction at the pore scale. And the patterns that we etch can be of variable complexity, so from very simple geometries with successive pores, or more complex geometries, and geometries that are directly drawn from imaging real works. And we can also include minerals in these micromodels. So this is just a classic setup for the microfluidics experiments, where we have our micromodel that is placed under a microscope. For flow visualization, the microscope is connected to a camera, and the fluids are injected either with a syringe pump or with a flow controller. The fluid that we use can be water, oil, gas, or acid. And with that, we obtain sequences of image of the flow. And one important step in this experiment is post-processing of the data. So with some image processing tools, we can detect the interface, detect how the pore geometry will change with time. And we also use one technique that is called PIV, so particle image velocimetry techniques, that allow us to measure the velocity fields in situ. So it is the principle of this technique is to seed the fluid, the aqueous phase, with microparticles that will follow the flow. And then from these kind of images, we can measure the velocity field in situ. So this is the velocity fields that we obtain from experiments that we compared with simulation for a single phase case. So these are the velocity profiles for both experiment and simulation. So here we compared experiment and simulation to be sure that experimentally we were measuring accurately the velocity field. And we are able to obtain velocity fields with one velocity vector every 2 microns. So then with these techniques, we can explore much more complex cases. And so today I will focus on the use of microfluidic experiments to study mineral dissolution at the pore scale. So a microcontinuum model has been developed by Cyprien Solène that is based on the Darcy-Buchmann-Stock equation, so to simulate the dissolution of solid minerals at the pore scale. So the idea was to investigate how the flow will change due to dissolution. So this approach has been presented yesterday by Sergi Molins because it's part of a benchmark effort. And to validate the numerical model, we needed to have high-resolution experimental data to be compared with the numerical simulation. So we set up these experiments where we have a channel, just a straight channel, and in the middle of the channel we have a crystal of calcite. And then in this channel we can inject acid from left to right and look at the dissolution of the calcite with time for different injection rate and different reactivity. And we can really follow the dissolution of the calcite. So with these experiments, we compared the evolution of the calcite crystal with time so from experiment and numerical simulation. And here this is the mass of calcite evolution with time for experiment and simulation. So really with this experimental setup, we were able to reproduce the numerical simulation. So we validated the numerical simulation. What is also interesting to see in these experiments is that the shape of the calcite during dissolution is really due to the hydrodynamic condition around the calcite, and we obtained this oval shape. So with that, now that the code was validated, we were able to perform simulation for more complex cases and for cases where we have an array of calcite crystals. And then for different injection rate and different reactivity of the media, we were able to show that we have different dissolution regimes that depends on the Peclet number and on the dam color number. So for example, at very low Peclet number, when diffusion is dominant over advection, we have a compact dissolution, so very uniform front. Then as we increase the Peclet number, we have one preferential path for the dissolution. And as we increase again the Peclet number, we have the emergence of wormhole and of ramified wormhole. And for low dam color number, so we have a uniform dissolution. So then we extended this work to two-phase dissolution. So when the CO2 that is produced during the reaction is not directly dissolved in the water, but also produce CO2 bubbles. So this is the same experimental setup, but now we have the production of CO2, so gas CO2. And so during the experiment, we see that at the beginning we have small bubbles of CO2 that will grow, they will coalesce, and at some point they will form a large bubbles of CO2, and that will detach from the calcite. And we observe the same successive events with a numerical simulation. So experimentally, we are able to measure, again, the mass of calcite with time. We can also measure the mass of CO2 with time, and we can also measure I did not show it here, but the size distribution of the bubbles with time. And so with that, again, we were using the experiments to validate the numerical code, and then we were able to perform simulation for the same kind of porous media that I was showing before. So here this is a simulation for the single phase for the ramified wormhole regime. And here this is for the two phase, when now here the timescales of dissolution of the CO2 in the aqueous phase is negligible compared to the timescales of production of CO2. So in this case, you can see that you have bubbles, small bubbles that are created. Again, they grow, they coalesce, and at some point they form flow barriers for the flow. So these CO2 bubbles, they really limit the transport of acid in the domain, and they prevent the emergence of wormhole, and they limit the average dissolution rate. So one conclusion of this work is that in the case of these two-phase dissolution, the Becklet-Dam color diagram should probably involve one other parameter, like taking into account the solubility of the CO2. So now I want to show you some ongoing work to show you that we can even get more details into the reaction with microfluidics experiments. So this work is based on this paper by Jenna Ponozami in Jülich in Germany. So in this paper, they did some colon experiments where so in the colon, they have strontium sulfate crystals, and then they inject barium chloride. So they will dissolve the strontium sulfate, and then we'll have barium sulfate that will precipitate. And because the molar volume of strontium and barium sulfate are different, we expect a decrease in the porosity and a change in the permeability. And what they observed in this work is that first, the Kozeny-Kármán equation that relates porosity and permeability underestimates the permeability change. And also that they observe that they conclude that they really need to take some pore scale processes into account in microscale models. So that's why we decided to perform microfluidics experiment to get more insight into the mechanisms in real time and in situ. So this is the microfluidics setup. So we have a reservoir here, and in this reservoir we inject crystals of strontium sulfate, and then we inject from here, we inject barium chloride from left to right. So this is how it looks like with the crystals. So this is the reservoir with the crystals of strontium sulfate. Here we have the presence of a fracture, and now we inject some barium chloride from inlet to outlet. And what is new in this work is that we use a technique, so where we use Raman spectroscopies that is coupled with microscopy to have really an in situ characterization of the different minerals that are present in the system. And so these are some of the preliminary results that we get. So we are really able during the reaction to follow the different minerals. So in red you have the strontium sulfate, in green you have the barium sulfate, and with time you see that the strontium sulfate dissolves and we have precipitation of barium sulfates. So this is one example of a 2D map that we can get from these experiments. We can also get 3D reconstruction of the minerals. We are now processing the images. So this is really an innovative experimental approach that will unravel dissolution precipitation processes in porous media. We can also use this setup to investigate, for example, interface mass transfer, CO2 transfer into the aqueous phase, and really, again, get more insight into the mechanisms at the pore scales. So with this work, I hope I convinced you today that experiments in micromodels, when they are associated with high-resolution post-processing techniques or spectroscopy techniques and numerical simulation, they allow for a better understanding of the mechanisms at the pore scales, their importance at larger scales. They allow to provide data to verify and to complete numerical models and to improve large-scale models. So I would like to thank my collaborators, so Cyprien Soulen, Tony Kovskech, Hamdi Chelepi, Wen Song, and Jenna Ponozami. And with that, I thank you for your attention, and I will be happy to take questions.
Great. Questions for Sophie? Sue?
I didn't quite understand. You did some that were one phase and some that were two phase. Like, what did you do different?
So, no, so experimentally, this is the concentration of acids that we change and the flow rate, and numerically, what's changed between these two simulation is kind of the solubility of CO2 in the aqueous phase. So the time scale of the CO2 dissolving in the aqueous phase is really negligible compared to the time scales of production of CO2 in this case. For the experiment, yes, we change the pH because we change the concentration of HCl. Yeah.
There was one more? Yeah.
Yeah, for the particle tracking, is there an open source code to do that yet? Or is that
So yeah, the code that we used is PIV Lab. This is developed for MATLAB, and you can find also some codes that are developed for ImageJ. So yeah, you can find different codes online. Yeah.
Great. Thanks, Sophie.
Thank you.
Okay, up next, we have Charlie Worth, who's going to be talking about microfluidic analysis of porosity occlusion due to microbial biofilm and mineral growth within shale fractures.
Click that? Okay, and there's right there. It doesn't show up here.
Exactly.
Okay. All right. Hello, everyone. I want to thank the organizers. It's really great to be here. I have a talk today on, it's more of a methods talk with some interpretation, but it has to do with a new microfluidic system we built based on shale. A student and a postdoc did most of the work. Lang Zhou's showing there. And then Ananda didn't send me his picture, so I just put a likeness of him there. And then I have quite a few co-authors on there. Rob Sanford's in the audience, I think, and a whole host of people, and the work is funded by DuPont. Basically, we're looking at shale, and I think y'all are familiar with the importance of shale and how it's become one of these critical kind of stratigraphic units that is being used both for oil and gas extraction, but also as a kind of a barrier to upward migration, both during oil and gas extraction, but also for carbon sequestration. And so trying to understand what the processes are that affect reactions and flow within shale fractures is, of course, important. These are a couple slides. The one on the left is just a cartoon showing shale fractures. The one on the right is kind of a cool image I found where they're looking at a fracture network within shale, and they put it into some water, and then it imbibes up into these fractures. And I thought it just illustrated how we can get these flow paths develop and how they have these kind of wettability that pulls the water up in this case. So at issue, at least what we were interested in, is how microbes grow in these fractures and how they affect fluid migration and also other properties that I'll get to later. Some of the main objectives, and I'm not going to address all of them today in this talk. One is to look at how these biofilms grow on these organic-rich shale surfaces. And you can imagine when you have organic matter contents up around 4% and you have a lot of hydrocarbons, perhaps you can have these toxic environments on these surfaces. Also looking at how we can quantify these rates of biofilm growth and mineral reactions. And in our case, we're going to be looking at driving this biofilm growth with sulfate reduction. And so we're going to have some reactions associated with that. And then looking at how that affects the permeability. So here's the setup. It looks really clean here. It's a mess when you're trying to get all the way to this step. But if you look, what you see on the bottom, kind of in the bottom center or leftish, is this shale microfluidic device. And there's a couple of features I want to point out in it. There's a clean single fracture. It's really a channel that we created down the middle. And since we want to have biomass growth, you can't have all the nutrients mixed in the tubing, or else everything just grows in the tubing. And so there's two inlet channels, and so you mix those nutrients when they come in. You have to have one limiting nutrient in each fluid coming in, or else biomass just grows up the tubing. And so that's why you always have two inlets when you're trying to grow in these systems. The way the fracture is created is we just cut shale, and then we're actually gluing it or epoxying it to a glass substrate. And so what that means is the optical path or the path of light can go clean through that channel. And so you have transmitted light. You're probably, or you may be familiar with, if you follow the microfluidics literature, work by Porter and others at Los Alamos, where they use this laser ablation technique. And they basically cut or etched a channel into different solid rock matrices. And we thought about that at first, but shale's black, and black doesn't allow light to be reflected back very well. And so it just looks black when you do that. And you say you can't see anything, you can't see the biomass. You could say, well, you could use fluorescence, but shale has lots of organics. And when you try to use fluorescence to see bacteria, well, the whole shale fluoresces. And so you can't see anything that way either. And so that's why we determined, or why we settled on just making a clean channel and having light be able to transmit through it. So there's a glass slide both below and on top of the shale. And that's the kind of the most straightforward approach that we could use to view bacteria, or really, even if you're trying to look at solutes fluorescing in a channel, you need a transmitted light to see that. If you look at the back side of this thing, we put it in a little manifold. We have the tubing, 2 inlets, 1 outlet. The outlet goes into a sulfide trap, which I'll explain in a little bit, so we can measure the amount of reaction that occurs, and then it's all mounted on a microscope. So we use a New Albany shale. It's a dark gray to black fine quartz clay, has organic matter contents up to 4%, and it has kind of these diagenetic pyrite fossils within them. And so you see that kind of dark banding on the left. Transmitted light, you can see the light in the dark indicating kind of some quartz. There's minor amounts of dolomite, and then you've got the clay and organics. And then on the right there, you see the SEM of this pyrite fossil. It's a marine-derived shale. We used a culture that we obtained from DuPont. It came from basically produced water from an oil field. That water was then put into a high pressure and temperature, or not too high temperature, but high pressure, and the temperature, I believe, was, I think it was around, I can't remember exactly, but somewhere around 40 degrees or so. We looked at we got that culture and we characterized it, and the culture was grown in the reactor on sulfate. And so as we expected and hoped, we found this sulfate-reducing culture, this desulfovibrio. Also present were, there were 4 dominant populations. There was an aminovibrio, which is, I think, an amino acid oxidizer, and then 2 different synergistacea. I'm not sure if I said that right. I'm not familiar with those, but of course I looked them up, and they produce hydrogen and probably do a bunch of other things that I don't know about. What we were really concerned about, or I guess interested in, was having a sulfate reducer, and so that's in that in the enrichment. We wanted to measure the pressure drop across the fracture, and this was quite a challenge. You know, you've got tubing that's going in that's 16th-inch tubing, and then you've got a little tiny channel there that's 250 microns. And so what you want to do is measure the pressure drop across the fracture and not across the tubing. And so basically you have to make sure that everything that goes into or out of that reactor has a bigger internal diameter than the width of the fracture. That's really the key. And that way you can look at what happens in the fracture. We originally went old school and did a manometer because it was, we had trouble finding a pressure transducer that could measure really small changes in pressure drop. And you can see the manometer, just 2 open tubes sticking up on either side of this microfluidic device. And what we would find is, as we would adjust the flow, the fluid level, because you know you only have like little microliter amounts of fluid in the reactor, but the manometers, they got a bunch of fluid. And so you get a pressure drop change, and it would take a long time because of the slow flow rates for the manometer to equilibrate. And we get kind of a qualitative reading, which was good, but the response was just on the order of, I don't know, every time something changed, you know, it'd be like an hour or 2 or more before you could see that things settle down. And so we found this pressure gauge, which has a really, really high resolution. And then the response was instantaneous. And so it gave really, it gives really nice readings. So when we set up the system then, we had a bunch of trials, of course, and failures. The success rates on these are not super high. So there's a little bit of an investment cost or startup cost. But we set up the system where we had lactate and some other volatile fatty acids going into one inlet, and then sulfate and cells going into the other inlet. And then they mix within this fracture where the channels combine, and then ideally we see biomass growth in that fracture. We first started growing them at a relatively high flow rate, and we weren't getting any biomass growth, so we thought that maybe the shear was too high. And so we came up with a strategy where initially we pulsed the fluid, and so stop, start, and that's shown in the bottom right, that plot, that's just flow rate versus time. And then once we start seeing biomass established, then we start doing a continuous flow, and then we start to increase the flow rate. Later on, we found that we could just grow them at a higher flow rate. We just had to just be more patient, I think. So the organisms are more robust to shear than we originally kind of identified. So here's results. This is basically 0 and 6 days, and I'll show you a sequence of time images here. So at 0 days, there's really nothing in the reactor yet. And at 6 days, they've had this stop, start. And when the organisms don't have continuous shear or continuous flow, they tend to be planktonic, meaning they aren't really forming a biofilm yet. Some of them are. They start to stick, but you don't really see that classic biofilm shape. But what we do see here is we see a lot of little individual organisms, and it's hard to see. I know you see kind of stipples, but I'll show you some better images in just a little bit as time goes on. But you start to see the biomass growing in that channel. And so that's just a piece of the channel near the inlet where these things are reacting. So here's 15 days, and there's these are the same location, but just two different focal planes. And I don't know, let me see if I got a mouse. Oh, I do have a mouse. All right. Over here, it's focused on the glass slide, and so you can see the bacteria sticking to the glass slide. And over here, it's focused on the wall, and you can start to see these biofilms. Here, it's a little clearer, growing on the wall of the shale. And so they're starting to colonize that, those shale surfaces. Here's farther on. This is day 15, what I just showed you. Day 27, it's thicker. We have higher flow. And then day 27, you can see it's quite thick. Down here is a little movie, and so this is the biofilm thickness. This is the planktonic cells and also things wiggling around in the glass. And you can kind of see, you see the movement in the kind of above where the biofilm is, where you have some of this planktonic cells, but there are also things wiggling around in the glass. And then you have the biofilm, which is more gooey and sticky and not fluctuating near as much, growing right on the shale. One thing we observed that's not apparent in the pictures is that as we increase the flow rate, the length of the biomass, or how far it grows down gradient from the mixing point, increases. And that's because we have limited nutrients, and so basically it's a trade-off between the rate of advection and the rate of reaction. And so if you assume everything's uniformly mixed here, the higher the flow rate, then the farther down gradient the nutrients will get before they're consumed by the biomass. And so as you increase the flow rate, we would get more and more biomass growing down gradient. So that was kind of cool. And so we haven't started to model this yet, but we want to look at then these rates of growth relative to advection on this shale with that data. We took apart the reactor at the end, and this is the surface where you got biofilm growth, and you can see all these little wormy little things. So that's cells growing on there. It's kind of cool. We also captured the effluent and measured sulfide, and this was something, an idea of Long and another graduate student, and basically they have mineral oil here. And you have, when you get sulfate reduction, you get sulfide, and sulfide, of course, is easy to oxidize. And so it would go into the mineral oil, and then that was a barrier to oxygen, and then it would drop down, and we had zinc nitrate. And so the zinc would react with the sulfide, and we get precipitates of zinc sulfide. And so we can measure the sulfide in the effluent that way. What we found is that at the low flow rate, we had all of the sulfate essentially converting to sulfide. And as the flow rate went up, we had some sulfate which appeared to be unreacted. I don't know how reliable these are, if our accuracy is within a factor of 2 or 1. The volumes are so small that it could be that this is just fluctuation in the data. So I can only say that we have reaction occurring, but I don't think I can say with confidence how much. We also saw these sulfate minerals, as you would expect, with these basically iron sulfides that were precipitating on these shell walls. The next step was we put proppants in the system, and the proppants, we basically injected these little sand particles into the system. Here they are, you can see them filling the whole system. These are all proppants along that shale fracture. And then this is 0 times 73 hours and 124, and this is just upgrading and downgrading. You can see upgrading, you're getting more and more biofilm forming on that. It's hard to see exactly where it's at, but there's kind of a slick movie here. And if you look at this, at first you think the biofilm's moving, but then you see it's just kind of pulsing. It's like these streamers that are attached to the grains, and they're kind of just moving with the flow of the fluid. And so they're attached and staying there. And when you have proppants there, there's a lot more of this biomass that's in the channel. And there we start to see some pressure increase in the system. And so if I go, well, that's an SEM image just showing before and after what these grains look like and how you get this biomass. Here it's collapsed because it's dehydrated, of course. But then if we look at the pressure drop, we get this characteristic behavior where when the proppants are in the system, we get, at some point, we start to get an exponential increase in the hydraulic resistance. And so that's something I think of concern, certainly. Or it could be good if it's a cap rock. So either way. So summarizing, biofilms and minerals grow on these shale and glass surfaces in open channels and don't appear to substantially block the flow. And growth is limited by nutrient availability and, in some cases, shear. When we have proppants present, we get a big increase in this, or decrease in the permeability, increase in the pressure drop. And we're looking at modeling this to look at the reaction rates and also looking at what's leaching out of this, out of the shale and the effluent under the non-biological and biological growth conditions when we have reducing conditions. And that's all. Thank you.
Thank you. That was really neat. Questions for Charlie? Oh, wow. Yep. Okay, over here first.
Very impressive work. I have a question about the aspect ratio of the shale channel gradients.
Yeah.
The width is 150.
It varies between 250 and 500, and the depth's 500.
So that the density is like the distance between.
Yes, that's right. It's like a square channel. Yeah, roughly. Sometimes it's 2 to 1, sometimes it's 1 to 1.
And kind of follow up on that, when you have proppants, obviously the velocity of the flow is much higher. How do you control that?
We have a syringe pump, so we can control the velocity or the average velocity through the system. Locally, I think, the velocities are going to be whatever the, how it distributes depending on the pore size. And so that's not something we've modeled. We don't control that. The proppants go in there on their own and they settle in there how they're going to settle. And so we don't have a high control over that packing within.
But you're using the same velocity to
I see what you're saying. It varies with the experiment. In some cases, we alter the velocity over time and we got biomass growth. In other cases, we're keeping a constant velocity. I don't know, I'd have to go back and look to see a direct comparison between when we don't have proppants and when we do and what the features are. There's a lot of variables in these experiments, at least how we've done it so far in trying to set this up, that I don't think I have a careful control at the exact, where everything was done from the exact same velocity from the beginning, and we have with and without proppants. Yeah.
I'm going to switch over. There was one more, maybe just quick question. Yeah.
Great talk, Riley. In the process of getting the produced waters out, did that change microbial community at all, or did you guys consider whether or not there were
Yeah.
or other things that don't like oxygen?
Yeah, certainly it changes it. So I call it an enrichment culture because once we take it out of the ground, we start growing it on sulfate. And in the ground, they grow on a lot of different things. And so you're also, while you're sampling, you're changing their pressure and their temperature. So, it's like you pick up something from the store and then it gets beaten around in the bag and, you bring it home and it looks a lot different from when you bought it at the store if it's breakable. And so it's quite a bit different. Maybe, the take home is that there's this desulfo vibrio in there that came out of the ground and we could grow it on sulfate, and that thing became a dominant part of that culture, and that's what dominated the sulfate reduction in our system. But there's certainly differences, and I wouldn't say it's even similar to what it was when it came out.
Great. Thanks, Charlie.
Yeah, thanks.
Okay, so we have one more talk, and as people have probably caught on to now, we've been moving in scale from the very large to increasingly high resolution, and now Xiaofan Yang is going to give us our final presentation where she turns and looks the other way from the poor scale to beyond. Thank you.
I would like to thank Han and Jenny for inviting me and really gave me a lot of pressure of getting my work done this year. So I'm going to talk about modeling. And I have a lot of frustration recently about how to model those flow and reactive transport processes because there are too many phases, too many processes, and too many data for use. So I really like the workshop that was held in Stanford a couple of years ago about imaging the critical zone, and also they brought up like 4 critical research questions, interfaces, couple of processes, and the properties and rock physics and the scolding. So that's basically the motivation of my current work. And now I'm kind of involved in a alpine modeling intercomparison campaign, which is called Interfrost, that gives a really beautiful logic and a strategy to develop your code, which you have to validate your code first, benchmarking, and then you take it to optimization, and then the next generation code development. And through the years, we sort of have successfully built at-scale models that we have both single-phase and multi-phase flow and heat models, and we incorporate them with heat transfer processes and the reactions, and also we have the biofilm, color, bacteria, those kind of things within our models as well. But how to integrate those models, scale coupling and process coupling are something that we want to tackle probably in the next decades. And although we have so many solvers and so many algorithms that we are kind of confident, I don't think that will give you a perfect model yet. We are constantly challenged by the how to balance your model with computational accuracy and efficiency. That's something definitely we need to consider as modelers as well. So I'm gonna present some of my recent works on modeling from different scales. First one is at the pore scale. Pore scale, I started my pore scale modeling with Tim Scheibe maybe a decade ago, and there are too many phases at pore scale. Multi-phase, and you have those interfaces that you want to simulate. How to do that, to tackle those phases. And I pick up a study, which is to investigate the interaction between biofilm growth and napole remediation. Because napole, as we know, that they are really common in oil spill, and they are really difficult to be removed. And also biofilm, I'm really excited to see Charlie's work on biofilm. And biofilm is just constantly and dynamically changing, which causes a lot of problem of our modeling. And for this work, we try to see the interaction between biofilm and the napole, the soil, and also the groundwater. So 4 phases, which gives you a lot of interfaces. And the equations actually are kind of regular and simple, per se, that we still are solving the Navier-Stokes equations with the convection diffusion equations. But all those kind of little things are there, the boundary conditions that we have to impose in our models to constrain those kind of multi-phase and multi-interface problems. And that's a pain. And we use lattice Boltzmann and combined with inverse boundary method for this modeling part, and we kind of generate like a synthetic domain, a computational domain that we have those red dots as soil grains, and the soil waters as blue, and also the green things are biofilms. We have a biofilm growth model, and also we have 3 napole bubbles within the system. So we kind of try to describe the the process between the nipple bubbles and the biofilm growth. And we emphasize that like within our modeling approach, the framework, considering the biofilm is really important because it's kind of something used to be ignored in most of the post-scale models. And I'm really looking forward to talking to Charlie about, comparing our modeling results to experiment because we don't have any yet. And going to the Darcy scale and the coupling processes, there are too many processes, hydro, bio, geothermal, other mechanical processes that we want to do. And because my current field site is in the high mountains, that we kind of try to model the alpine processes in high mountains and to see their responses to perturbations. And our critical zone observatory is actually the first CZO observatory on the Qinghai Tibet Plateau, which is called the Qinghai Lake Basin CZO. So other than that, it's on the plateau. It also has the largest saline lake in China on the plateau, and we have different systems of observations across the basins. And what I'm trying to do is to model the thermal, the THMC processes undergoing freeze thaw, because there is a large distribution of permafrost in this region, and also snow is another thing that we need to consider as well. And of course, we are dealing with challenges as the heterogeneity, the multi-scale, and also because of due to the FT cycles, we have the phase change between ice and water, and also those FT cycles will change the morphology of the soils. And we are developing a groundwater model that incorporates the FT cycles, which we call them Darcy TH-form because it's based on the open source platform. And we just resolve the 3D recharge equation with Darcy's law and also the heat transfer. And for the phase change and the FT cycles, we have those soil freezing functions that we can use to do that in our model. And we also this is my own hobby, that to write a software based on Qt and Python that for students and other people that are not friendly to modelers, that they can use the interface instead of programming. And yeah, we have a series of benchmarking cases for our newly developed models that we have two simple benchmarking cases first. One is the frozen inclusion thaw, which is actually an ice cube melting with time, and we compare the temperature evolution with different codes and other analytical solutions. And the second benchmarking case is the thallic, which is commonly exists in permafrost, and we also model the evolution of the temperature with time. And then we take the code to the lab and the field. The first laboratory experiment is a freezing experiment that we have the temperature difference in our soil column, and we compare our modeling results with the experiment in terms of temperature as well. And as you can see, the transient time history data shows a pretty nice agreement between the model and the experiment. And once we've done that, we're kind of confident that this model can be used to the field. So we use the open access, the available data of the Hehe River Basin, which is actually a cryosphere observatory. And they have a 10-year of data for soil moisture, soil temperature, and also heat conductivity and water potential. And all of those data you can download from this paper that's online already. And then we use that model to compare a 5-year soil moisture and temperature data, and with the in situ observations out in the field. And it gives you pretty good agreement of soil temperature, and we have some discrepancies of the soil moisture for sure. Well, one of them, the measurement is not perfect, and also in our model now, we still keep the porosity and the permeabilities as constant through the time, which should be corrected because keep changing with the soil properties. And also, what we are doing now is we want to see the impact of snow melt in this cryosphere region, that we currently still using a simple degree day type of snow model that we just impose the flux into our modeling domain, which from the results you can see that actually the snow melt gives you a considerably difference other than without considering the snow model. Due to the simplicity of the snow model, we are still trying to do both field and laboratory manipulation experiment, working with Heidi Stelzer and the Berkeley lab to see if we can have a better snow model in our system. And yeah, data. There are too many data. I mean, what kind of data? I mean, I'm talking about enforcing data and those data that we need to use in our models. I mean, what kind of data are the best, and what kind of data are the best available and we can use, and what about the resolution, something that we need to consider. And actually, the first piece of work that I've done this year is to use PowerFlow CLM with Reed Maxwell to see the effects of groundwater pumping and their responses to the land surfaces in the North China Plain, because the North China Plain is famous of the overexploitation of the groundwater, and as you can clearly see from the Great Satellite. And we simulate this groundwater pumping for different in different scenarios, and what we want to see is if the effects of groundwater pumping on the ground surface temperature and the energy fluxes. And I'm not going to talk about the results for this piece of work because my frustration are on the data sets. And at least all the forcing data and other data that we use to spin up the model to get this started, and these are too complicated and they are not perfect and they're not very easy to use, which actually motivates us to see our next work is to evaluating the source data, the multi-source data, and the impacts of the subsurface heterogeneity on those kind of large-scale hydrologic integrated modeling. So my student, Zheng Lu, actually he's sitting there, he conducted a systematic study of using different combinations of currently available forcing data in our study domain, which is in the He River Basin, and we want to see how those data impact the results, how the subsurface heterogeneity behaves for the integrated hydrological modeling. So if you're interested and have questions, please go to Zheng's talk the day after tomorrow. And yeah, I think we are kind of running out of time. So with that, I'll just quickly have some take-home messages. For our modelers, we sort of have think that we have successfully built at-scale models, and benchmarking and intercomparison is something that we always have to do before we use the models. And I haven't talked about upscaling in my current in this talk yet, but because I'm struggling with upscaling between different scales. And yeah, and the model coupling is still challenging in both physical and numerical in every way. And also, I still want to address that we, as modelers, would agree that we always try to model the perfect, but we don't really have a perfect model yet, that we want to collaborate with the community for a better model. And with that, I will conclude my talk. Thank you very much.
Thank you. Questions for Xiaofan? A lot of scales in 15 minutes.
Too many models.
No. Thank you. I'm just keeping an eye on the clock, and I think we're going to get kicked out. But I wanted to say very quickly, thanks to all of the speakers again, if we could give them a round of applause. And Hong and I are very fortunate to be part of a new research coordination network that was awarded to Alexis Navarre-Sichler, and we're working with her along with Kate Maher. So keep an eye out for the next few years' worth of reactive transport as a means of promoting education and model application in the earth sciences. Thank you.